Okay, good morning, everyone. Let's dive right in. Those taking the course for graduate credits, you are now working your way through the differentiable assignments. So far, so good. Okay, assignment 6 for the undergrads, doing a little bit of refactoring, some spring cleaning before we push on. All good? Okay. All right then. So back to our brief survey of the history of evolutionary robotics. We almost finished lecture 9 last time, looking at 4 of the initial minimal cognition experiments, trying to evolve some of the building blocks of intelligence into an autonomous machine. We got through 3 of the 4 experiments last time. We'll finish the 4th and final one, and then push on to the last experiment in the minimal cognition series, which is yet another building block of intelligence, active categorical perception. Okay, so again, the idea behind minimal cognition: make a very, very simple robot, as simple as you can, simple physics, simple environment, simple body, handful of motors, handful of sensors, and let's set up some environments and some fitness functions that select for some of the building blocks of intelligence, like perceiving affordances. Then we looked at discriminating between self and non-self. And we ended last time by looking at this example of a robot that can evolve short-term memory. It can move left and right along the bottom of the screen. It's got 7 proximity sensors, but the twist in this experiment is the moment the motors receive non-zero values and the robot starts to move, lights out for the robot. Can't see anymore. All 7 of the proximity sensors report 0 for the rest of the simulation. And we ended last time with this figure here. As usual in the minimal cognition experiments, we're playing back the best CTRNN that we got back from the evolutionary algorithm, the most fit CTRNN, drop it back into the robot a whole bunch of times under different environmental conditions, and let's see how well that evolved CTRNN allows the robot to generalize to situations it did not see during evolution. In this case here, they were dropping an object that falls straight down from the top of the screen, starting at different horizontal positions at the top of the screen. What is the robot doing in this case? How well is the robot doing in this case? Pretty well, yeah? There's a few hints here about what the robot is actually doing when armed with this CTRNN. How is it solving this problem?
Something to do with like the lines being like where the walk will be and the amount of time it takes to move.
So the robot definitely knows exactly how much time it's going to take for the object to hit the ground and how to move to get there. Yeah? Any other ideas?
It just seems like, because like the closer it is, like where it's like the less units and the later it starts to move. So it's like it's trying to time it perfectly, so it'll hit it like right the last moment almost.
Absolutely. Yeah, it's kind of showing off again, right? It could get there faster, but it's sort of taking its time. You'll notice it does a particularly poor job with the edge cases. The 2 drops from the upper left and the 2 drops from the upper right. And those trajectories are drawn in gray to show that at the end, the robot wasn't exactly where the object hit. It's having a bit of a difficult time with these cases. Why do you think that is?
Is gravity like an acceleration in this case versus like a linear speed? And so like for cases where it's close, it's not really being affected by the acceleration versus the far one.
You got the tail end of it here. So this is a very simple physics engine. There is no acceleration. The objects are just falling straight down. But you're right. There's something about the edge cases that's a little bit harder for the robot.
Could just be like motor speed. Like it just can't get there.
It could be motor speed. Again, I'm hiding a lot of details from you. This robot can move a lot faster than you see here. It's choosing to move at this. So it's not limited by its speed. Yep.
Is it not allowed to hit the walls?
There's no walls.
Or-
There's a black box here, but it could move indefinitely to the left and the right. Any other ideas? Why is it having a hard time with these edge cases?
Is it out of bounds of the sensors, like almost?
Remember that these proximity sensors, before they turn off, they're pointed up in a cone. So again, like a cat's whiskers, as the objects are falling straight down, the object is stroking the tips of these proximity sensors. The values are firing at non-zero values for a short period of time, but then the object passes underneath the cone of perception here. And of course, the robot could try and move to see the object again, but it can't, right? It goes blind. So in these 4 cases, the robot is only seeing the object for a very short period of time. It's got less information, and clearly it's kind of making an approximate guess about where the object is eventually going to hit, and it's not perfect, right?
From this point, would giving it the ability to like rotate its field of vision, would that like just totally complicate it and make what currently exists not work?
Probably. So if we suddenly gave this evolved CTRNN a different sensor motor apparatus, so suddenly the CTRNN is getting values from sensors that move or stay on when it's expecting them to turn off, probably not going to do very well. And again, this is the elephant in the room for all of AI and robotics research. If something different happens in the real world from what happened during training or evolution, who knows what's going to happen? But usually something not great is going to happen. Okay. I think in the interest of time, we're a little bit behind. I'm going to skip over this. This kind of is more or less what we've seen before. The robot does okay, but not perfect. Okay. Let's have a look at one last example here. So this is again one evolved CTRNN, and in this upper left plot here, they're going to drop objects from above again, but they're going to drop them at a diagonal. They're going to take the same evolved CTRNN, put it back inside the robot a whole bunch of times, drop the object a whole bunch of times from directly above the robot, but those objects are going to fall at different angles. What does this one evolved CTRNN that we've been looking at throughout here cause the robot to do under these environmental conditions?
It seems to like move and then stop and look again and then move.
It seems to move and stop and look again, except the robot can't look again. Remember that the moment it starts moving, it's completely blind.
So it kind of goes to the point that it predicts it'll fall to it goes to the point where it predicts it'll fall to on like the diagonal path.
Okay.
Not accounting for the actual angle of the current block being dropped.
Could be. Any other observations? What's with this zigzagging motion? You're right, it stays still. So all of these trajectories that don't change angle until a certain point, this is the robot staying still and presumably looking at the object and quote unquote thinking about the object, integrating some information over time, combining what it's sensing with memory, and then it starts moving, which is what these jinking lines here mean. Why is the robot moving and then reversing course and then moving and reversing course and getting there right when the object hits?
Is it like when someone throws a ball and kind of move from side to side to maximize the amount of space you can cover? Is it that sort of thing where you're trying to kind of, you're not quite sure, so you go over area?
You could, right? If your eyes are open, right? You're going back and forth and trying to estimate. Remember that as the robot is jinking back and forth, it started moving, it's completely blind.
Can it see when it's not moving, like in between
No, it can only see at the beginning. So sorry, this is a good point. It sees as long as it stays motionless. The moment it starts moving, it goes blind. And if it stops moving again, it does not suddenly see again. It remains blind. I'm sorry, that's an important detail. It's blind throughout these periods in which it's moving back and forth, but successfully ending up where the object is. Why doesn't it move straight towards the object at a constant rate, as it does in the case when the object is falling directly from above? I'm throwing you a fastball very early in the morning. This is a tough one. It's a bit of a trick question. There's no reason. There's no benefit to moving back and forth, and getting to the object and catching it, compared to moving at a constant rate and catching it. The only thing we said is catch the ball. Make sure that your horizontal distance is 0 when the object hits the ground. Be where the object is. The fitness function says nothing about how the robot should move to get there. So in retrospect, we get back things that seem very inefficient, right? Why this extra motion? I wanted to spend a minute just focusing on this point because this is one of the inevitable results we get from anything that's evolved. You get some things that are inefficient as long as they're not an actual drag on the organism or the machine yourself. Your bodies and my body are filled with inefficiencies. We're not perfect. Mother Nature often leaves things just as they are unless there's a very strong reason to clean up or make that behavior or that piece of physiology more efficient. This might matter for robotics. We don't want robots that are moving around in the real world at very high accelerations and decelerations and doing extra stuff. We'd like them, generally speaking, to do just what we want them to do and no more. It's not easy, it's not trivial to make sure that robots always do what we want them to do in sort of the most efficient, calm, constant, predictable way. Mother Nature doesn't necessarily work that way.
Is there an idea just like across most of the things of like just minimizing like energy expenditure?
Okay, minimizing energy expenditure. So we may or may not get to our lecture 11 today on the biomechanics of motion. Absolutely, when we're talking about physical robots that are big and heavy that have to move around, energy efficiency is pretty important. So things like this tend to go away, but there are other more subtle ways of being inefficient and a little bit unpredictable if you're the result of an evolutionary process. But a good point. This is just sort of one of the more obvious examples we're going to see of this side effect of evolving machines in this course. Yep.
If you wanted to sort of, let's say, train out some of that inefficiency, would you choose to adjust the fitness function or create scenarios where that efficiency is naturally not selected for, or maybe both?
That's a great question. So if we wanted to get rid of it, where in the evolutionary process would we put something to get rid of it? We could build a term into the fitness function that penalizes for joules, actual amount of energy that's used, or we could create an environment in which the best way to do the right thing most of the time is to move in an energy efficient manner. It's a great question. There is no one good answer to that. It is still an area of active investigation. If you want a machine to be reliable, energy efficient, don't accelerate, decelerate suddenly. How do you go about ensuring that that happens under conditions that it didn't see during evolution or during machine learning training? Not an easy thing to do. Good question. Okay, let's keep going. All right, fourth and final event that we're going to look at. This is my favorite one. This is selective attention. This is something that we humans also struggle with, not an easy thing to do. Let's have a look at our minimal robot here. Again, we have a minimal robot that has two rockets that exert thrust to move the robot back and forth along the bottom of the screen. You'll see that its 7 proximity sensors are drawn with solid rather than dashed lines. This robot does not go blind when it starts moving. It can move and sense at the same time. As always, we're going to drop some objects from the top of the screen. In the selective attention experiment, we're going to drop pairs of objects, but these objects are not connected together. They fall independently. As you can see from the black dashed arrows here, this particular object is falling down and to the left at a slightly slower velocity than this object, which is falling down and to the right at a faster velocity. Given this cartoon, which of these two objects is going to hit the ground first? One's closer but falling slower. One's closer to the bottom of the screen but falling slower. The other object is further away from the robot but falling faster. Which one is going to hit the ground first?
Is there like, it would be the object that has the least distance to fall to velocity ratio.
Correct. Did you have an idea in the back there?
I was just gonna say, we can't know until we know exactly how far away they are, exactly what their velocity is.
Absolutely, right? So this is a cartoon. You gotta have to eyeball it, but it gives you a sense of the problem here, the challenge, right? You're eyeballing this. The robot's gonna have to do more or less the same thing. It's gonna be able to collect information and try and figure this out. It's got to select which object to attend to. It's going to see these objects, and these objects, one's going to be closer to it than the other. Which one does it go chasing after first? The fitness function over here, as you can see on the right-hand side of the equal sign, there are two terms. And it shouldn't take you long to figure out that these two terms are are rewarding for the robot minimizing its horizontal distance to the first object when that object hits the ground, and then minimize its horizontal distance to the second object when the second object hits the ground. By first and second object, we mean the first object to hit the ground and the second object to hit the ground. Make sense? Okay. Okay. A student who took this course several years ago actually tackled this as their final project and coded this up in, at that time we used Open Dynamics Engine, a different physics engine. So here is an evolved CTRNN controlling a robot in the ODE physics engine that has evolved to successfully exhibit selective attention. You can see that some of these environments are easier than others. Question?
So with this, is all that matters that the two circles are in view at some point? Like,
All that matters is they are in view at some point, right? If one of these objects never touches any of these 7 proximity sensors or are never registered by any of the 7 proximity sensors, the robot by definition doesn't even know there's a second object, let alone know where and when it's going to hit.
And is the number of like kind of, I guess recursive, that's not the word that you use for like the connections to give it memory.
The recurrent connections in the CTRNN give the robot memory. Yeah.
Is there like a limit on how far, like, do there have, like, to remember like 50 iterations down the line?
That's a great question. So if you incorporate recurrent connections into a CTRNN, and hopefully most of you have realized that, first of all, this CTRNN does have recurrent connections because the robot needs memory in order to solve this task. Great question. How long can it remember for? Turns out that even with a few, we won't do the math on the board, but even with a few recurrent connections, if the synaptic weights of a C tier and N, and the time constants are tuned correctly by evolution, it can remember for a pretty long period of time. It keeps passing what it remembered from the previous time step on to the next time step. And it keeps doing that. You can kind of actually work it out with pen and paper if you're interested. Clearly, it does need to remember for quite a while, right? I see both, and I decide that I think this one's going to hit first. So I go over to capture this one, and I can no longer see this one at all. I need to remember a bunch of things. Which side of my body was it on? When did I last see it? Where was it? How fast was it falling? And off I go. And depending on how these are falling, I might need to go do something over here for quite a long time from the robot's perspective before it's able and allowed to go back and do that. Yeah? I don't know about you all, but every morning I open up my to-do list and then my stomach just drops. The number of things that are on there. I look at the one at the top. Is that the one that's going to hit the ground first in that any given day? Maybe not. I move it down, move another thing. Then suddenly a text comes in. Does this go on the list? What am I doing after class? I don't know. Selective attention. Tricky for humans to do, right? What are you going to do with the rest of your day? What's on your to-do list? How are you to prioritize? I often chase after one task and completely forget what the other one was and try and recover. Not an easy thing to do. Okay. David was very successful with this project. He and his robot make this task look easy. As you can probably guess, it's not easy. By all means, tackle this for a final project, but it is not an easy option. Doable, clearly, but not easy. Okay, so what exactly is it that makes this problem so difficult? Like many non-trivial tasks us intelligent machines try and tackle in the real world, you can break that hard problem down into multiple, slightly less hard subproblems. There are two important subproblems that any agent needs to be able to succeed at in order to succeed at selective attention as a whole. The first one is the passing objects problem. There may be one object that is initially further away from me. It feels like a less urgent task. I can worry about it later, but oh, wait a second. There's something about that distant, either literally or figuratively distant task that tells me, actually, I should attend to that one first. It's actually going to be the one that's going to erupt sooner in the future than the other one. I've got to figure that out first. I can't just chase after the one that's closest. Wouldn't that be nice? That would be a very easy way to deal with lots of things throughout your day. Not so simple. Then there's the object permanence problem. One of you comes up at the end of class and asks me a question verbally. I tell you that I'm going to respond to it later in the day when I get to my email. I go do 1,003 other things and completely forget to write you back. The object permanence problem, right? How do we mentally juggle things that we've got to remember to go back and attend to later? Not easy. In the minimal cognition experiment, we can make these cognitive problems actually literal and watch the robot evolve the ability to solve them or not solve them. Make sense? Okay. All right. So, as always, in the minimal cognition experiments, they evolved and evolved and evolved and evolved C tier and N's to get better and better at the task, and then plucked the most fit C tier and N out of the last generation of the evolutionary algorithm, dropped it back into the robot 1, 2, 3, 4, 5 times. And during those 5 evaluations of that evolved C tier and N, they exposed it to increasingly more difficult environments. So in this particular task, we can actually quantify the difficulty of an environment based on whether or not that environment challenges the robot to neither one or both of these subproblems. Here we go. Let's have a look. Let's start by taking this one evolved CTRNN. We're going to drop it into the robot and put that robot into an easy environment. It does not need to solve the passing objects problem, not PO, and it does not need to solve the object permanence problem, not OP. What does it mean for the robot to not have to worry about the passing objects problem?
The lower one is, or if they're moving at the same speed.
They could be moving at the same speed. Whatever it is, the one that's closest is going to hit the ground first, right? Just go after the closest one. That makes it easy. Okay. It also doesn't have to solve the object permanence problem. What does that mean? What does that tell you about this environment?
They're going to be moving at roughly a similar angle, so both will always be in view.
They could be moving at, the two objects could be moving at a similar angle so that they're always in view. However it is that the objects are moving, the robot can more or less easily keep them in view. This particular figure here is drawn so that you can see that reality. So again, it takes a little bit to parse some of these minimal cognition figures, so we'll take our time here. You'll notice that there are two straight black lines descending from the top of the figure. One of them descends to halfway down the figure, and the other straight black line descends all the way to the bottom of the figure. And vertical axis here is showing us time increasing as we descend this figure. What do those two straight black lines represent? The path of the object, right? Why does this first black trajectory stop at a certain point? What is that telling us?
That the robot caught it.
Not necessarily the robot. We're not even talking about the robot yet, just the two objects.
Is it that the other object hit the ground already?
That whatever this object was, it was falling straight down and hit the ground at this time. Yeah? This object over here is continuing to fall, and it hits the ground at this time, the end of the simulation. What is the jinking black trajectory representing?
Robot.
The robot's movement, right? So tell me what the robot did in this situation. How well did the robot do in this situation? It's showing off again, right? It figures out very quickly that it's this object that's going to hit the ground first, which is the closest object to it. And it's jinking back and forth underneath the object. And then the moment that it, quote unquote, catches the object, what does the robot do? Straight over, and again is showing off, going right, staying right underneath the object and catching it. What do the two gray parallelograms represent? What are the authors illustrating here?
The darker gray represents the object that's going to hit the ground second, and the lighter gray represents what's going to hit first.
You're right in the sense that the two parallelograms correspond to the two objects, but not where they're going to hit. That's what the straight black trajectories are telling us.
Is it the view angles for them?
It's got to do with the viewing angles. It's got to do with the robot's perception. What exactly about the robot's perception?
Is it where it could hit?
That's a good guess. They could have probably visualized where they think the robot is going to hit.
The cone of view, the sensors.
The cone of view. So if you imagine taking a horizontal cut at any height through one of these parallelograms, what that means is that the robot could be at any point along that horizontal cut and see that object. The light gray parallelogram corresponds to the object that's going to hit first. So let's take this horizontal cut right at the top of this figure. This means the robot could be anywhere at these horizontal positions at the bottom of the screen and comfortably see the object. Why are these parallelograms narrowing as time progresses in the simulation?
Because the object's getting bigger, so
The object.
In reference to the robot.
True. The object is getting bigger from the point of view of the robot.
Also, since the sensors are arrayed in the cone, the field of view for the robot gets smaller and smaller.
Absolutely, right? As these objects are approaching the stem of the cone of perception, there's a narrower width through which the robot can move and still see the object, assuming it wants to see it, which it doesn't necessarily need to do. Okay, everybody now see how to read these figures? Okay. All right. You'll see that the jinking trajectory stays within the parallelograms the whole time. Actually, while there are two parallelograms, the robot is staying within both of them, which means it sees both of them at the same time. Everybody see that? So no object permanence problem. It's easy for the robot to watch both objects while waiting to catch the one that it knows is going to hit the ground first. Easy peasy. The evolved CTRNN enables the robot to solve this task, no problem. Let's make things a little bit more difficult. I'm going to take the same evolved CTRNN, play it back in a different environment in which now we're going to expose it to one of the two subproblems. We're going to drop these two objects at a different angle and velocity so that now the CTRNN is going to be challenged to solve the passing objects problem, but still doesn't need to worry about the object permanence problem. When does this passing objects problem occur?
The dashed horizontal line.
The dashed horizontal line is telling us the moment at which the further object, which is falling faster, passes the closer but slower moving object. Yeah? How is the robot doing? Yeah? Is it still showing off? Kind of. You'll notice that at least above the dash line, so this is when the object that's going to hit first is still further away from the robot. It kind of looks like maybe the robot doesn't know, right? It's kind of jinking back and forth between the two objects that are above it. And it's still doing that for a while, but drifts over and catches the first object, and then goes over and catches the second one. When does the robot know what's going to happen? When does it realize that the object that's further away is going to hit the ground first?
When it's no longer further away.
Looks that way, right? The robot could actually be lazy in this case and just wait. Wait until this happens. Sort of watch both of them and say, aha, now there's an object that's closer to me and falling faster. Now it's easy and I know what to do. Thinking about thinking is misleading. It's not quite clear. The robot might actually know beforehand. It's just not telling us that with its behavior. Who knows? Okay, let's look at the converse case. Same evolved CTRNN, no passing objects problem. So the object that's closer to the robot at the beginning is falling faster, but there's an object permanence problem. How so? Yep.
When the first object lands, it's in a situation where the robot cannot see the second object.
Absolutely, right? So when the robot catches the object that hits first, that the cone of perception can see that first object, but now the robot is outside the darker parallelogram, so it cannot see that object. Did it know where the object is? Absolutely, right? It goes racing over here and gets there with more than enough time to capture the object. Okay, let's make things hard. Passing object and object permanence problem. You can see the two straight black lines are falling away from one another, so the objects are falling and also increasing their relative horizontal distance as they fall. There's our dashed horizontal line. So at one point, the further, faster object passes the closer, slower object. How does the robot do in this case? It does well, right? It's kind of showing off. It knows. It gets there in plenty of time and then races over to catch the other one and gets there just in the nick of time.
For the robot moving back and forth, is it like possibly being impacted by randomness, where it's not exactly certain that like it's calculating the velocities correctly, so it's keeping its options open to try to catch one object or the other?
Yeah, that's a great question. So the question is about, is there randomness in the environment? And maybe it's not sure. Again, I've left that detail out. No randomness in these environments. These are minimally complex. They've tried to remove everything they can, including randomness, which is something that exists in the real world.
Do we know how the robot remembers where the other object is, or is that something that was just kind of evolved in the CTRNN?
It evolved in the CTRNN. Who knows, right? You could probably crack this open and spend 20 years trying to figure out what's going on, and it's hard. It's hard to see it in the brain. We can only really see it in the behavior of the robot.
Did they have to build some kind of framework for it to remember this, or did they just start remembering? You know?
All they told the robot, all they told the evolutionary algorithm is evolve a CTRNN that minimizes these two terms. That's it. The evolutionary algorithm is discovering sets of synaptic weights, time constants, biases, gains that allow the CTRNN to allow the robot to achieve the task. Nothing in here explicitly says do it by remembering, do it by moving back and forth, and if you're uncertain, be sure to go chase after it as soon as possible, take as much time as you want. None of that. Just here's what we want, you figure out how to actually do it.
Is the speed of the robot at all a limiting factor of like I see it has this like long diagonal line. Like,
yeah.
If the motors were like more powerful, could it just get there quicker?
That's a good question. It's unclear from the paper. The authors were insufficiently detailed. It's not clear whether this robot could actually move faster. In the video I showed you from David's final project, that was the fastest the robot could move. It was definitely hustling. In here, I'm not sure. Other questions or comments? Okay, so we made things pretty hard on the robot, and it still did excellent. In the fifth and final case, we're going to expose it to the passing objects problem and the object permanence problem again, but we're going to make both of those sub-problems harder. How? You can actually see how this task is more difficult than this task.
The robot can only see both of them at the very beginning.
Absolutely. There's only a very short time window in which the robot can see both at the same time. What happens immediately after that window of time has elapsed?
It goes straight towards the one.
It knows, right? Somehow. Now, what it could have done, there's nothing in here that says the robot has to look at both at the same time and compare the direction in which they're falling and the speed at which they're falling. It could, in theory, if it was quick enough, go back and forth and look at one and then look at the other and then look at one and then look at the other and still solve this task. But it looks pretty much like this robot has, quote unquote, decided very quickly. The CTRNN has evolved to compare when it's looking at both objects at the same time. Races over and catches this one, but this one is falling away from where the other one is. This robot quickly reverses course and gets back just in time to catch the second object. All good? Okay. All right, that concludes our lecture on minimal cognition. In my personal opinion, it's a shame. Not other people in the community have followed up on these experiments. This feels to me like a good way, solid way to make progress on making incrementally smarter and safe machines, right? What you just saw was a whole bunch of different CTRNNs that enabled the robot to do individual building blocks of cognition, you could imagine revisiting the minimal cognition experiments and combining some of these fitness functions, evolving robots to selectively attend and distinguish between self and non-self, and then also perceive affordances, and. Maybe we could construct a very long-running evolutionary algorithm where over evolutionary time, we keep adding terms to the fitness function to select for more and more of these cognitive building blocks and gradually build up smarter and smarter and smarter machines, while ensuring that in a lot of different other conditions, they still do more or less what we expect.
How well do these things actually like build on each other though? Like, it's like
Nobody knows. They were all done in isolation. How well do they build on one another? Is it easier to evolve a robot that selectively attends and then evolves the ability to perceive affordances? Or is it easier for evolution to evolve a robot that perceives affordances and then evolves the ability to selectively attend? What order should it learn these things in? If you're interested in machine learning, there is a whole branch of machine learning outside of robotics that studies exactly this. It's called curriculum learning, right? In our faculty meetings, we argue all the time about what order of courses you all should take. You need to take CS, ABC, and then CDE. It's not so obvious sometimes to know in which order to learn things so that you build more complex competencies on top of simpler ones. Tricky to do for humans, also tricky to set that up for machines. Yet another open problem in robotics and AI. Okay, so we're going to dive into lecture 10 now, where we're going to look at a fifth and final building block of intelligence, which is active categorical perception. This task is not really minimal, because the robot that we're going to look at is definitely not a minimal robot. It's got a pretty complex physiology. We'll come back to the robot in a moment. But first, let's talk about ACP. I want you to join me in the following thought hypothetical experiment. I'm going to place several objects in front of you, but you're blindfolded. And I'm going to give you a task, which is separate the round objects from the edged objects. You've got blindfold on, so you don't know what these objects actually look at. You need to solve this task. You need to categorize, you need to perceive and categorize the round objects from the edged objects. What do you do? What actions do you perform to categorize between the round and the edged objects?
You might try to like roll them.
Most human subjects, when they're given this actual problem, they grasp the object, pick it up and hold it. I don't know. But put their hand on top and go back and forth like this, and what happens? If you were to place your hand on top of each of these objects one after the other and do this motion, what happens?
Some of them roll, some of them don't.
Some of them roll and some of them don't. Suddenly, we have a binary category. Some are rollable. Remember affordances from last time. Some of these objects are rollable and some are not. If you look at these objects, obviously, there is no binary distinction, right? There is a gradation from round to edged. Where does this category come from? It's almost like a magic trick. There is no set of round objects and a separate non-overlapping set of edged objects here. And yet, when you interact with them, there it is. Where does this set come from?
Well, it comes from the affordance that I can roll this, I cannot roll this.
The category is not necessarily in the objects themselves. The category is in the relationship between, in this case, not just an observer, but an active participant who is manipulating the objects, right? You categorize things tens of thousands of times every day, right? Friend, foe, sittable object, non-sittable object. We're doing it all the time. We categorize things in the world, but in the world itself, There are no categories, right? They arise from the way that we interact with the world. And Mother Nature has tuned our bodies and brains over millennia and millennia to exploit that phenomenon so that we keep going and survive and reproduce and so on. So the idea behind active categorical perception is as we move about in the world, or as we'll see in a moment, as machines move about in their world, they have a need to do this, to understand the affordances of things. What things are safe and what things are dangerous. Mother Nature has tuned our bodies and brains so that we interact with those things in a certain way that causes us to discover that category and hopefully discover it quickly, especially if we're trying to distinguish between safe and not safe. I have a 2-year-old at home and he's very interested in the knives that are up on the kitchen table, right? He's got to figure out the difference between edged and non-edged objects. There's an infinite number of actions that he can choose in which to learn that lesson. Most of them are not a good way to learn that lesson, right? We have been tuned, luckily, so that we choose particular actions and ways to interact to learn these categories as quickly and safely as possible. As we do, as we learn to literally reach out and manipulate objects in the world around us, over time, in the human species, over years and years, we learn to start to do that interaction more and more from a distance. I'm categorizing which of you is actually paying attention and which isn't, and luckily I don't need to reach out and actually manipulate you to figure it out. I can categorize from a distance. How did we learn to get so good at categorizing from a distance? We learned when we were little creatures by doing it actively, manipulating objects and feeling these literally feeling these categories arise. It's easier to categorize objects when we physically interact with them than it is to categorize objects by looking at them from a distance. It probably doesn't feel that way to you because you've been doing it for a long time. It feels like categorizing things in your world from a distance is super easy. Thinking about thinking is misleading. What's it called when we're younger, we're doing things in a certain way where it's easier, and then as we get better and better at solving that easier task, that sets us up to be able to do the same task but in a more difficult way. We've heard this phenomenon, we've encountered this phenomenon several times already.
Is this scaffolding?
This is scaffolding. In psychology, the dominant theory is that for a lot of intelligent agents, ACP scaffolds distal perception, being able to distal categorical perception, being able to categorize from a distance. It's still a theory. There's a lot of evidence from years and years of observing little humans and big humans. This is something we could test in robotics. We're not going to test that today. We're just going to look at a robot that's evolved to do ACP. Sound good?
Is that even like a reasonable thing to distinguish between active and distal categorical perception? Because it's still an action to move your eyes across.
Great, yes. So Cam has swallowed the red pill. Everything is embodied, right, in an action. Even when we look around in the world, you are saccading. The muscles in your eyes are moving your eyes, so your eyes are jumping around and touching different things in your visual field. Yes, it's not that it's non-embodied, and it's not that it's passive. It's probably not a good term. You're right. It's all active. Let's say proximal, going up and actually doing it close up and personal, and distal, doing it from a distance. That would have probably been a better pair of adjectives to describe these two behaviors.
When it comes to like in robots, is the fineness of touch a lot more difficult to do than like distinction visually though?
Great question. So super easy to slap a whole bunch of cameras onto a robot and get tons and tons of high resolution data at a high frame rate. Not so easy to make skin for robots so that when the robot touches something, it gets rich, high-resolution data. There is a whole subfield of robotics basically filled with chemists and materials scientists and mechanical engineers that are making sensitive skin for robots for exactly this reason. Okay, all right. So regardless of whether we're talking about organisms or machines, if an organism or a machine, an agent, wants to succeed at ACP, that agent has to choose actions that reduce within category differences. When you push your palm left and right across the top of these objects, the ones that are rollable start to feel similar to you. You feel this object and this object and this object and this object all rolling. They're all rolling. You're feeling the collapse of within category differences. These objects are different, geometrically different, but when you interact with them in the right way, that difference feels less. Make sense? You're also trying to magnify between category differences. Rollable objects feel similar, and non-rollable or slidable or pushable objects feel similar, and those two sets of sensations are different. There's an infinite number of ways that you could touch or manipulate these objects that do not do these two things. They all feel different. They all feel the same. We're looking, and we're going to see in a moment, evolution is going to look for ways to move the robot so that that robot reduces its felt within category differences, and that those actions magnify the robot's felt between category differences. Make sense? Okay, off we go. All right, let's talk a little bit about the robot itself. We're going to, as we've seen now several times, we're going to evolve populations of CTRNNs. We're going to take each CTRNN and drop it into this robot. And each CTRNN, we're going to evaluate that CTRNN 8 times. We're going to replay that CTRNN 8 times on the robot. In the first 4 cases, in the first 4 environments, we're going to place a sphere underneath the palm of the robot. But for each of these 4 sphere placements, we're going to place the sphere at different rotational angles, which doesn't make a lot of sense because it's a sphere, it's radially symmetric. So from the robot's point of view, it doesn't feel any of those differences. In the 5th, 6th, 7th, and 8th evaluation of the CTRNN, we're going to place an ellipsoid underneath the robot's palm, a little egg. And in each of those trials, we're going to start by placing that egg at a different horizontal angle underneath the palm of the robot. Everyone getting what this game is? The robot's going to have to, quote unquote, tell us, is it touching a sphere or an ellipsoid? Sorry, I misspoke. We're not going to play each CTRNN 8 times. We're going to play each CTRNN 16 times. We're going to start by setting the robot's arm and hand to this initial position 8 times for these objects. And then the 9th through 16th trial of a CTRNN, we're going to start those trials by putting the robot's arm and hand to this set of initial conditions, and then again expose it to these eight objects. Question?
Why would changing the bending of the arm have any,
Why did they do that? Why didn't they just evolve the CTRNN to distinguish between spheres and ellipsoids with one initial setting of the arm and hand? Good question. Why?
Does it come back around to flexibility so that it can, if you were to take that same CTRNN, you can do it in different scenarios?
In different scenarios. They're going to try, they want this robot to be as robust as possible, that under different conditions of the object itself and possibly the robot, and therefore different conditions about the initial relationship between the robot's pose and the object, that it can tell whether it's in contact with a sphere or an ellipsoid. Make sense? Okay. All right, let's have a look at the robot's body itself. This is, if you look at the title of this paper, Active Categorical Perception in an Evolved Anthropomorphic robotic arm. Anthropomorphic meaning in the shape of an anthro, in the shape of a human. So they're building in some additional human physiology here. Let's look at it. Luckily for you, this should be relatively familiar. We've got a shoulder, elbow, and wrist. And I'm sorry, this might be difficult to see from the back of the room, so I'll just turn out the lights for a minute. You'll notice that there are actually two joints at the shoulder. In this robot, they're going to simulate each individual joint is a rotational joint, like we've talked about many times before already. If we put two of them together in the shoulder, that allows the robot's shoulder to do this and to do this. So the robot's shoulder can basically do this. You have a third degree of freedom in your shoulder, which is this one, right? So you can do this. The robot can't. It can only do this. So it's not quite human, but it's getting closer. Question?
So in simulators, do you actually just put two joints in the identical location with like different?
Yeah, so you can try this. You can actually try this out in PyBullet if you want. You can create one object and connect it to, or you can create one link and connect it to a second link with a joint, where that second link is just a little sphere sitting inside the shoulder. And then you connect that little sphere to another joint, to a third joint, connect it to a third link with a second joint that's at exactly the same location, and you can get this. If you think about it and play around with it in PyBullet, you can add 3 in the same place, and you can get a full shoulder joint. Okay, so we've got 2 motorized joints in the shoulder. We've got a third joint in the upper arm. It's not your elbow. There's your elbow. It's not your shoulder. Show me what it's simulating here. It's this. Elbow is the 4th motorized joint. That one makes sense. There's another one in the forearm. 5th one in the forearm. Show me which one that one is. We're getting our stretching in this morning. Yeah, it's this one here. That's number 5. 6 and 7. Wrist. This and this, but not. That's number 5, right? 5, 6, 7. Good, I can see you all waving. There you go. You got the idea. Okay, so we're up to 7 motorized joints. We're gonna arm this robot, no pun intended, in a moment with the CTRN. We've got 7 motor neurons, and then we got a whole bunch of things going on in the hand. In the human body, there is one part of your body in which most sense organs are localized. Second most part of your body in which you have localized sense organs, the palms of your hands, because we're primates and we learn a lot about the world by grasping objects like this, right? Okay, let's see how this works. We've got, you might be able to see this from the back, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 additional joints, which are causing the arm to pull together. I'm sorry, I misspoke. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are these little gray circles. These are 10 touch sensors in the hand. If you look carefully, you'll see there's a whole bunch of light blue cylinders. These are all joints. These are not independently motorized joints. You can move your shoulder and not move your elbow. You can move your elbow and not move your shoulder. You have independent muscle groups in your arm. I challenge you to move I'm going to turn the lights back on now. I challenge you to move your distal phalange, which is the tip of your finger, and don't rotate your intermediate and proximal phalange, the 2 bits of your finger that are closer to your hand. Most of us cannot do it. There are some people that can. So we've got 20, I don't know how many it is. There's a whole bunch of joints, motorized joints in the hand. They're going to assign to all those motorized joints 1 motor neuron. At every time step in the simulation, and I'll play the simulation for you, that motor neuron is outputting one floating point number, and that floating point number is going to all of the motorized joints in the hand simultaneously, which causes the robot's hand to do what? This, yeah? Now, of course, we can do this. Our fingers are independent. They're going to kind of sweep that detail under the hood. So a fair bit of human physiology built into this robot. Why did they do it? I don't know. Maybe just for fun.
Could you explain again how they get one motor neuron to get all of the
Yes. So there's 1, 2, 3 joints in the thumb, and then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 in the remaining 4 fingers. So there are 15 motorized joints in one hand of the robot. So far, so good. So you can imagine coding this up in PyBullet, in PyroSim. 15 motorized joints. In everything we've seen so far, there was always one motor neuron assigned to each motorized joint, right? In this case, there's one motor neuron that fires, and that whatever that floating point number is coming out of the motor neuron, it's copied 15 times and sent to the 15 motorized joints so that they all apply identical torque, which causes this. This robot cannot move its fingers identically. Make sense? Okay, all right. That's the body of the robot. Let's switch and look at the brain of the robot. This robot has a total of 148 total neurons in the CTRNN. So its brain has 48 neurons in it. This is a CTRNN. So down here, we've written out the ordinary differential equation for the ith neuron. Since there are 48 neurons, that means there are 48 differential equations that describe the behavior of the CTRNN for this robot. So far, so good? Okay. I like this figure from the paper because they bounce back and forth between the mathematical description of a CTRNN and a visual depiction of the CTRNN. So these two things are identical. If you still feel rusty about ODEs and CTRNNs and time constants, this is a good figure to put a few minutes of effort into. Okay, here we go. Let's start with the visual depiction. This should be familiar. We've got a sensor layer here. This robot has a total of 22 sensor neurons in there. And here's the uppercase I sub I. This term is sending in that sensor value to that sensor neuron. We've got 23, 24, 25, 26, 27, 28, 29, 30. We've got 8 internal or hidden neurons. And then we've got a whole bunch of motor neurons up here. So actuators, motors means the same thing. And then we've got 2 neurons out here, the last 2, neuron 47 and 48. These are the categorization neurons. The robot is going to light up these 2 neurons to tell us whether it thinks it's in contact with a sphere or an ellipsoid. So far, so good? Okay, we've got 7 proprioceptive sensors in the arm. Where are they? What are they reporting? What in the arm are they reporting? Position or angles of the joints, right? Proprioception is joint angle. So we've got all the 7 arm angles coming into the brain of the robot. We've got a total of 10 tactile sensors. The 10 touch sensors in the palm of the hand, and this is how they're distributed throughout the palm of the hand of the robot. And did I get that wrong? Hand proprioceptive sensors. We've got 5 proprioceptive sensors in the hand. Where are those 5 proprioceptive sensors?
Tips of your fingers?
It could be the tips of the fingers. It's not clear from this picture. It's the curvature of the finger. Remember that the finger, the different parts of the finger are all curling in together. So we've got 5 numbers reporting the curvature of the 5 fingers. But I just finished telling you that each hand has one motor neuron which closes or opens the entire hand. So why does it need 5 different numbers?
It's kind of like the difference, like in a, so when it tries to squeeze, some objects are gonna like, I guess like the hand squeezing would like meet resistance.
The hand is going to meet resistance depending on, exactly. The minute it interacts with the object that it's trying to categorize, those curvatures of the finger are going to change, right? That's some pretty important information. What's that?
It tells you like the shape of something.
Does it? Does it tell you the shape? Maybe. Maybe. Depends on how you grasp the object.
Yes.
I could grab the object, the top of the sphere and the ellipsoid like this, not so much. I could go like this, and maybe it does. There's actually an infinite number of ways that I could grasp an object. Some are better than others at helping me to reduce within category differences and exaggerate between category differences. Yeah? Yeah? Okay. Okay. So those are the sensor neurons. They're all sending their floating point numbers into the hidden neurons. What is this arrow that's curving back on itself telling us? Recurrent connections. So this robot may evolve the ability to remember, if that's useful.
Why do we need 2 categorization neurons? Should we only need 1?
Yeah, I'm hiding that detail from you. This is the whole punchline of this entire experiment. The way they're going to handle 47 and 48 is everything in this experiment. We'll get there in a minute.
For like the architecture of the CRNN, like, is there a reason they only have one hidden layer versus like wouldn't having just a little bit more complexity there?
Yeah, so that's a good question. We could add multiple layers of hidden neurons and turn this into a deep CTRNN. As the deep learning revolution has taught us, there's good reasons to do this. They didn't do this in this experiment. And this experiment was published when the deep learning revolution was just starting. Okay, all right. We've got 14 motor neurons assigned to the arm. That's strange. 14 motor neurons, but there's only 7 joints. There's 2 motor neurons assigned to each joint. This we also have not seen before. This seems strange. Why? Any ideas?
Is it so it can hold it in specific positions because they'll have 2 locking up at certain spots, so like it can get like stuck here or here. It's like trying to keep moving all the way in, they'll just go like stop.
You're getting close, right? So we've got 2 motor neurons that are sending values and kind of tugging on the same motorized joint. Remember that they're trying to create an anthropomorphic robot, a robot that that instantiates some human physiology. What human physiology are we talking about in this case?
The fact that our muscles can only pull in one direction.
The 14 motor neurons in here, although it's not shown on this figure, they only output positive numbers. They pull with more or less force. This is known as antagonistic and agonistic muscle groups. In all the major muscle groups in your body, they're all arranged in pairs. Your bicep, when it pulls, it flexes your arm in. Your tricep, when it pulls, you extend your lower arm. Muscles are like ropes. They can only pull, they cannot push. So all the major muscle groups in the human body are arranged in pairs in which they antagonistically or agonistically pull on the motorized joint. That's what they're adding here. Do they actually need this detail for this experiment? Absolutely not. They probably just put it in for fun. Okay, hand actuators. I told you that there's one motor neuron per hand. I lied. There's actually 2. Why 2?
Is it like a push and a pull?
Not a pull. Push on the inside and then a sorry, a pull on the inside and a pull on the outside. Same thing. They're simulating roughly agonist and antagonistic muscle pairs in the hand. Okay, so someone asked in the back about neurons 47 and 48. Let's have a look at those now. So any questions about the CTRNN? It's actually pretty much like everything we've seen before, just with some additional anthropomorphic details. Okay, we've got 5 minutes left, so let's dive in and talk about neurons 47 and 48. As was pointed out a moment ago, they could have got away with just one neuron, and the investigators could have decided that the robot gets a fitness point if, when in the presence of a sphere, this neuron is negative, and when the robot is in the presence of an ellipsoid, this neuron should be positive, for example, right? They could encode that as the way for the robot to tell us whether it thinks it's in contact with the sphere or an ellipsoid. They could have done that. They didn't do that. They've got two neurons. With two neurons, you could do something like if the value of neuron 47 is larger than the value of neuron 48, that's the robot telling us it thinks it's in the presence of a sphere. If the value of 48 is larger than the value of 47, that's the robot telling us it thinks it's in the presence of an ellipsoid. You could also do that. It's not what they did. Let's see what they actually did. They did something much more complicated, and I'm going to draw this for you. We're going to draw this visually in 2 dimensions. We're going to draw a plot where we're going to look at the values of neurons 47 and 48. I'm going to put y sub 48 and y sub 47 to just remind us that we're going to be looking at the value of the 47th neuron and the value of the 48th neuron. Let's imagine at the beginning of a simulation, we put the robot's palm on top of a sphere. The robot doesn't know yet whether it's in contact with the sphere or an ellipsoid. And at the very first time step of the simulation, we're going to put it in contact with a sphere. It doesn't know whether it's in contact with either. It's the very first time step of the simulation. So the value of 47 is 0, and the value of the 48th neuron is also 0. And now the robot starts moving. The CTRNN transforms sensation into action, and suddenly the value of neuron 47 and 48 changes to a pair of non-zero values. Time step 0, time step 1, time step 3, 4, 5, 6, 7. And we get this trajectory in 2-dimensional space, where the trajectory is showing how these 2 values change over time, over the lifetime of a single simulation of the robot in contact with the sphere. So far, so good? If any of you have taken a dynamical systems course before, this is a way to visualize a dynamical system, meaning any system that changes its dynamics or its motion over time. What is this visualization called? There's a name for it. No? Okay. If you do take a dynamical systems course, this is a phase diagram, just in case you hear that term. It's a nice way of showing how a system changes over time. Okay, let's imagine this is the robot in contact with the sphere, and we're going to look and we're going to look at the lowest and highest value of 47 and the lowest and highest value of 48 during the last 5% of the simulation. So this is the last 5% in here. We started with t sub 0 down here, and we went to t final down here. This is the, this is the maximum value that 47 ever achieves during this short time window. And the minimum value of 47 during this short time window is this little point here. during this short time window here, the lowest value of 48 is this point here. And during this short time window, the maximum value of 48 is this point here. That gives us this little bounding box in two-dimensional space. And we're going to call that little bounding box R sub E. It's the rectangle that we place around the spherical object. So far, so good? Okay. Seems a little strange for a moment. Bear with me. Was there a question?
Yes, are you only looking at the curvy part of the graph?
We're looking at, remember that each point on this trajectory, it represents those two neuron values at that point in time. So yes, we're taking the last little curvy point, but it's really, we're trying to ask what was the maximum and minimum value of these two neurons at the last moment. We're gonna challenge the robot to tell us whether it thinks it's in the presence of the sphere or ellipsoid during the last 5% of the simulation time. We're going to give it the rest of the time to quote unquote figure things out.
I don't know a ton about them, but does that diagram eventually like have an orbit or like?
Yeah, you got it right. So we can get into the dynamical systems in which it drops into an orbit and repeats itself. If you plot the position of the Earth in three dimensions, it will start to repeat itself in a phase diagram. Okay, we're out of time for today, so let's pause here. You have a quiz due tonight. Undergrads, you're refactoring. Grad students, you're starting in on differentiable simulation. Have a good rest of your week.